Good afternoon, ladies and gentlemen. Can you? Yeah. I'm so much happy to be able to visit Surabaya. This is the second time for me, maybe the 5 years before. No. Okay, thank you very much. Yes.
Everybody loves you very much.
Okay. Thank you so much. I'm so much happy to be here again. And thank you very much for very kind introductions, Eni-san. Today, I'd like to just talk about the multi-scale modeling of the structural concrete. But this is just so, it used to be my hobby of these topics. Because maybe about 20 or 30 years ago, I'd like to have some sort of the concrete engineering libraries, material science, construction technologies, structural engineering, and so on. These are very much valuable information for infrastructure development. But how to effectively use this knowledge for practical problems. Maybe I think this was the first starting point of my talks. Then today, I'd like to just introduce these things. And nowadays, someone in some fields, this type of method is applied to the real practical problems. So then I would like to call for your opinions, ideas, and criticisms. Just before my talk, that's just self-introductions. I'm more than 60 years of age, or almost 62. I graduated from the university in 1980. At the times, I started my work in the master program, doctor programs. At the times, I start some research on the constitutive models of concrete. In those days, many people said that this is not the research of concrete, as a matter of fact. More, structural mechanics and so on. Then, first of all, when I was a student, I was not accepted by the Society of Civil Engineering in Japan. So this is not the concrete engineering, this is some sort of mechanics. But anyhow, occasionally, I could be a member of the concrete engineering. Then after that, some structural dynamics and earthquake has become my major work. And during these times, I could be involved in the development of self-compacting concrete, super flowable concrete. Very nicely, so I could be a part of these teams and the first patent holders of this SCCC. Anyway, after that, I could have a time to study and teach at the Asian Institute of Technologies in Bangkok. This was the very much important time for me, just 2 years services. But at other times, I could have a chance to talk, to think about the future directions. Just at other times, I have to study, I have to teach in the morning for concrete materials, concrete constructions, afternoon, structural engineering. It's so much big problems, but very much interesting. But how to combine this knowledge for real problems, that can be some good point. Then after that, I started to talk about this, to think about the multi-scale modeling and simulations. But after that, there was a lot of big problems. 3 near-field earthquakes. Many people died in Japan, maybe. And again, some big problems. That is a tsunami attacked this city, about 20,000 people died. And 2012, at the peace times, infrastructure collapsed and some people died. Then, through this process, the durability, lifetime assessment, bridge decks, anyway. I have been involved in these projects. Then I try to use my knowledge, but you see, please understand that we have to solve the problems. We have to have some results. Even though we study so hard, but if this cannot be linked with the real problems, it's big problems as a civil engineers. Then I try to be a civil engineer. Then multi-scale modeling is one of the platforms of this thinking. Yeah. So when you, maybe I think you have a very good eyes, you can see some sort of crackings, in fact. But if you are super strong eyes, you can see some entrained air bubbles. But when we have an optical microscope, so we can see that. But I can say that this is the views of the concrete solids by using the eyes of electrons. But this is SEM pictures. But anyway, so we have some water, some ions, calcium, several minerals. But these substances have some link with the more large-scale behaviors. Sometimes some crackings and some other materials is very important for stiffness of the structures. Then these are linked with each other. But at the time, when we open the books, a lot of variable information existing still at this point. But how to link with each other in order to solve these problems? And furthermore, so these are the part of the structures. So this is some pictures of the urban highways in the capital city of Japan, Tokyo. You can see so huge amount of traffic. It was constructed about several years ago, but still we have to use this one. Some mechanical engineers said that we can buy the very nice cars at this moment, right? Something like that. But we have to drive old-fashioned cars for the infrastructures. Nowadays, these infrastructures are replaced with a new one, but it's a very important thing. As a matter of fact, you know that this is one of the heavily used infrastructures in the world. According to the statistics, maybe about 1 million vehicles use these infrastructures. Maybe this is still not a national record. And the second heavily used infrastructures is San Francisco Bay areas. This is about 30% of this one. Yeah, then still almost all very much old, but we have to live with these infrastructures. Okay. Then, well, this is just pictures, but anyway, I have no time to talk about this, but when we look at the behavior of the cement and water, we can see some crystals. But this information is very much important for creep and shrinkage. Sometimes the creep and shrinkage have much to do with the risk of the crackings. But if the crack or risk of cracking, but if the crack occurred, sometimes water or oxygen gas, chloride can pass through this one. And then this is also impact to the microscopic worlds. Therefore, these are mutually interact with each other. Then I think in the field of mechanical engineering and chemical engineering, some multi-scale, multi-physics, multi-chemophysics is becoming some sort of the good platforms because now the performance of computers is so much higher. Therefore, I have been working together with the students also, Yanni-san as well. But about 20 years ago, many engineers said that, oh, that's a play of the academicians. No way to use this technology for the practical real worlds. But at that times, I am so much comfortable because this is my hobby. I have no idea. I don't have any intention to use this one for the practical problems. Yeah. As a matter of fact, my mentor is a very, very nice engineer. He has no theory, he has no theory, but very good solutions. Therefore, I feel jealous. It is impossible for me to be like him as a civil engineer. Therefore, I decided to do that. But nowadays, some people, some engineers start to use this one. Maybe the world is changing. Then now, today, I would like to discuss how this type of knowledge will be used. But please understand for academia, different discipline amalgamations is very much important. This is not easy, but I think that within this concrete engineering, within the civil engineering, these amalgamations of knowledge should be done. Yeah. Then this is some sort of the background. Anyhow, it is. But during this time, about 5-6 years ago, we came to the very big shock. So, as I said, at the crisis times, many Japanese people die because of natural disasters. But this is the accident. This was the accident of the collapse of the infrastructures. This is at peacetime, and some people died. So this was the first experiences for Japanese peoples after the World War II. Therefore, many people suppose that those infrastructures is not like air, it's not like water. So if we don't have any maintenance, we don't have any care, so it will be lost. But as a matter of fact, I have to say that in the past 30, 40 years, many people are so much interested in constructing new things, but so much money are addressed to new things development, but very few for maintenance. Then with this one, cabinet office headed by the Abe, Prime Minister Abe, so seriously consider. Then maybe in the past 40 years, biggest fund came to the civil engineering. Yeah, so in order to solve these problems. This is a 5 years project. This was headed by my senior Professor Fujino, of the former professor of the University of Tokyo. Then I was a part of this project. Then I was asked to have some, life assessment method for infrastructures. Then about 12 universities and about 120 engineers and professors are involved for that. And also, this is the biggest funding for us. But at the same time, we have to have some results. Then for maintaining infrastructures, we made some sort of inspections. We check. After that, diagnosis and assessment of the life. According to the results, we decided some countermeasure, repair or some protections, and also we did some sort of some actions. And this action, the results should be validated or checked. This is a maintenance cycles. But in order to do some maintenance cycles, this life assessment is very much important. We found out in the past, when we have a crackings, when we have a leakage of the water from the infrastructures, okay, let's go to the place, let us repair. But this was the current former situations. But if you can come to the clinic, and if your medical doctors behave like that, maybe you encounter a big problem. Because when we have a bleeding from the knees, that's okay, washing these knees, putting something. But if you have a bleeding from the ears, right, there are several possibilities. One is that some small blows. But another possibility is the bleeding from the brains. Therefore, in these situations, when your doctor would put some paste like that, oh my God, there is a possibility of the bleeding from the brains. But in this case, it's all right. But at that times, like this, when crack was found, okay, repair. When we found some sort of corrosion, repair. But I think no discussion about the whole health conditions. Then some knowledge of the material science and structural engineering are necessary to have a sound, judgments. This is a balance. Today, I'd like to discuss these applications of the solid science, thermodynamics, cloud, and mechanics, and so on for this one. At the same time, please understand we have another very important information. Because in the past, we have a lot of maintenance informations or some record of the crackings or corrosions after the constructions. There's a big data of the maintenance. Therefore, we can learn from the past experiences. Therefore, roughly speaking, if the bridge was constructed about 30 years ago, if we have some sort of a cracking, so according to the experience, we can say that maybe 20 years left If we have no repair, maybe 10 years or 20 years, some problem may come. This is the statistics. But at the same time, there are deviations, right? Therefore, sometimes we have to check each individual infrastructures. Yesterday, Anson said that high cholesterol is not so good, but a very nice nasi goreng is good with high cholesterol. Very tasty, yeah? It's all right. It's all right, but I think when you come to the clinic, a doctor said that, okay, when you can take, if you take nasi goreng every day, so your life will be something like that, like this. But anyway, this is based upon the statistical informations. But of course, people's health condition is quite different each other. Therefore, when you come to the clinic, the medical doctor check your blood pressure and the proteins of the urines and also some weight and also heart rate and so on and so on. Then statistical information and also diagnosis of each particular person, individual persons, these are combined together. But I think this was not on the line. This used to be, this has been existing. Therefore, we can judge the average values, but sometimes some bridges or infrastructure are far from the average, sometimes. Then this one will be now combined together. Today, I would like to talk this one. Because one bit experience exists because this statistical experience is very important. But maybe you know that about a few years ago, some old and very famous cable-stayed bridge collapsed in Italy. Yeah. But at that time, so according to the experience, they said that maybe okay, but not so good. Maybe okay, not so good. Around 10 or 20 years, they have a lot of discussion, a lot of meeting, a lot of committee. Then during the discussions, structure collapse. Yeah. But of course, when we consider the data of about 1,000 bridges, maybe this bridge can serve more. But individual situations is far from the average. In this case, we have to have some two eyes. This is today's proposals, and this is now the background of using the multi-scale modelings. So then this is one of the results. I'm going to talk about this issue. My colleague, Professor Ishida, who visited here, with these statisticals and also multi-scale modelings, we also estimate the remaining life of the bridges along the urban highways in the Tokyo areas. You can see that some red one is a really red, just like traffic signals. And also yellow, this is cautions. And green or nothing is maybe all right. Then you can see that some part is almost red. Some part is good. But please understand this line has been constructed only within the 2 or 3 years. And also the similar design code was applied, same design code applied. But the result is quite different indeed. So there are several reasons. One is that bad constructions, bad quality assurance. The other one is the very heavy traffics, especially when you can see some intersections. A huge amount of traffic comes, then the damage is now accumulated. Anyhow, maybe you can understand that total average, we can say that another 30, 40 years is all right. But for bridges or for a road, if only one bridge collapses, this is the end of the service, right? Therefore, we cannot play with average values. We have to pick up some killer factors, indeed. Then, about 20 years ago, I suppose that multi-scale model would be the play, or just a hobby of the scientists, but nowadays, the situation changed. But I would like to just introduce some step by step. In 1980 to 2010, in the academias of the engineering of the civil engineering, structural engineering, reinforced concrete structural behaviors have been discussed with the computer simulations. First of all, many people challenge some shell structures with cracks and yieldings. But these are computed based on the cracking models or some shear transfer modelings or bond modelings and so on. But anyhow, there is nothing new because after cracking, stress is not transferred. Okay? And also yielding occurs and cracking, so plasticity occurred. Therefore, maybe all students may attend the undergraduate programs. When you use this in-plane theory and after cracking, no stress transferred, the same things, but only the difference is that crack direction, several directions. In the undergraduate programs, only one directional crackings, but that's all. Of course, calculation is becoming complex, but there is nothing new because originally Hognestad of the American University, he's not a professor of the university, Hognestad, maybe very famous professors, established the design method of bending. So this is just an extension. And also, this has been applied to the very shear problems with some deformation localizations. This is a case of the shear failure of the different span lengths and so on. Maybe around 1990 to 2000, many people challenge these type of things. I suppose that there are some computer softwares circulating in the world. This can be captured like that. Then, of course, I proposed them to use this past experienced knowledge for the practical problems for life assessment. And then from 2000 to 2008, this type of technology will be extended to the fatigue problems with many cycles. Because life assessment, maybe you know that the fatigue is very representative things of the life of steel structures and also concrete. Then according to the number of cycles, gradually, deformation, displacement is increasing. Like this. At the same time, this is a case of the cracking around 170 cycles, but when we wait about 500-600 cycles, these cracks are growing, and finally failure occurred. Roughly speaking, this is the static capacity of the members, one-time failure. But when you introduce about 80% of the static capacity, the structures can survive. In this case, about 100 times like this. When the so amplitude or stress level is about 60% of the static capacity, the structure can survive up to the 1 million cycles. But I think within this, on this floor, I think some students enjoy some trainings, some sort of the muscle trainings, right? Maybe you can say, please imagine that if you have a 30 kilogram, one time 30 kilogram, right? Therefore, but when you have 20 kilograms, maybe you can do 100 times, right? When this weight is more small, many times. Therefore, this curves is almost similar to the human bodies. Yeah, when you can have some lift up 100 kilograms, this is your capacity. So you can lift up 80 kilograms, maybe 10 times. When this is 50 kilograms, you can, like this, right? Therefore, you can imagine that, so concrete structures have some fatigue, similar to the human bodies. But I think I heard from the medical doctors, our body was made by bones, muscles. At the same time, that bones is made by calciums and some others. But concrete, calcium and silicate, non-organic materials. I heard that non-organic material have similar like this. But the organic material, we have quite different stories. Therefore, concrete is non-organic materials. Our body is made by non-organic materials. Therefore, we have a similar fatigue performances. Therefore, when you have this type of imaginations, this can be used. So, but I think this can be applied to the traffic moving load. So this one is a shot of the moving load fatigue experiments. When we apply the fixed point load, the slab or structures can sustain many cycles. But, but when this load is in motion, like a traffic, so much fatigue, so tough. About 100 times fatigue life is shortened. This was found in 1975 or 6. But at that times, bridge engineers, of course, know that fatigue is a big problem of bridges. But at other times, they apply the fixed point load. And one of the urban highways in Japan, the first time, so they investigated the fatigue life of the structures, a lot of experiments. Then, so they made some public, open public opinions. These structures are designed, maybe the life of the structure, maybe 1,000 years, or more than 100 years. But after this press release, this infrastructure was open, and about 7 or 8 months after the openings, structure failed. Then other times, it's okay, engineers said that life must be 100 years, but in reality, less than 100 years. But it is very much natural. When we introduce some moving load, life is almost 100 times shortened. This was not known in those days. Therefore, the fatigue problems is becoming very big problems. Then, in order to assess the lifetime assessment, this type of simulations is very much important things. Therefore, the government decided to construct runway on the sea. So putting a lot of piles, so many piles. After that, about 14,000 plates are arranged on this one. We have to think about the remaining life of the infrastructure, which was already used. When we construct a new structure from now on, expected life. But some old structures have been used in the past several decades.